Did you know that Toyota manufactures over 10 million engines each year, with many lasting well beyond 300,000 miles? Today we're going inside their factories to see what makes these engines outlast the competition. What if I told you Toyota's reliability begins before a single part is manufactured? While many drivers assume engine durability comes from assembly quality or design choices, Toyota's engineers know a fundamental truth. Exceptional reliability starts with the raw materials themselves. Unlike many manufacturers who source materials primarily based on cost and weight considerations, Toyota implements an extraordinarily rigorous material selection process. Their metallurgists and engineers work with specially formulated metal alloys that must meet exacting specifications, often exceeding industry standards by significant margins. Like master chefs selecting only the finest ingredients for a signature dish, Toyota's material scientists accept nothing less than perfection for their mechanical recipes. In an industry obsessed with lightweighting and cost-cutting, Toyota deliberately chooses materials that prioritize longevity over immediate advantages. While competitors transition to all-aluminum construction with ever-thinner castings, Toyota frequently opts for more substantial materials, including cast-iron engine blocks in many models. This added weight provides critical advantages in thermal management and structural integrity that become evident as vehicles age. The material properties Toyota prioritizes create a foundation for extraordinary durability. Cast iron dissipates heat more effectively, preventing microscopic warping during thousands of heating and cooling cycles. Its additional mass absorbs vibration more effectively, reducing stress on internal components and bearings. Even Toyota's aluminum components differ from competitors, containing precisely calibrated amounts of silicon, copper, and manganese. Proprietary blends developed through decades of research to enhance resistance to thermal expansion while maintaining excellent casting properties. Toyota's evaluation process borders on obsessive, subjecting potential materials to extreme conditions that simulate decades of real-world stress. Before approval, alloys undergo temperature cycling from -40 degrees Fahrenheit to well above operating temperatures, while simultaneously facing exposure to coolant, oil, and combustion byproducts. Engineers analyze grain structure and crystalline formations, focusing specifically on how materials will perform after 15 years of continuous use, far beyond the warranty periods most competitors design for. This long-term perspective creates tension within Toyota's engineering departments. Marketing teams might prefer materials allowing for impressive horsepower or fuel economy ratings, but Toyota consistently resolves this tension by prioritizing durability. The connecting rods in Toyota's 2.5-liter engines exemplify this philosophy, using thicker, stronger forgings with additional material in high-stress areas instead of the lighter designs that would improve immediate fuel economy figures. Toyota's specialized testing equipment compresses decades of use into accelerated time frames. Components undergo testing to destruction, identifying failure points that engineers then eliminate through improved material selection. This approach establishes the foundation for Toyota's exceptional reliability record. Engines routinely exceeding 300,000 miles when competitors struggle to reach half that lifespan without major repairs. The material science behind Toyota engines represents a fundamentally different value proposition in the automotive world. While other manufacturers optimize for initial specifications or purchase price, Toyota designs for total lifetime ownership cost. This philosophy extends throughout the entire vehicle, but begins with the careful selection of raw materials. Elements that will reliably carry families, commuters, and adventurers for hundreds of thousands of miles without complaint. Beyond superior materials, Toyota's approach to engine design follows a philosophy that might seem puzzling to performance enthusiasts. While most manufacturers chase headline-grabbing numbers, Toyota deliberately takes the opposite approach, designing engines that appear almost underwhelming on paper, but deliver extraordinary reliability in practice. Have you ever wondered why Toyota engines often seem underpowered compared to their competitors? This represents a deliberate strategy rather than an engineering shortcoming. Toyota intentionally operates their engines well below theoretical maximum capacity, resembling a marathon runner who maintains a steady pace rather than sprinting to exhaustion. In an industry fixated on maximum horsepower from each cubic inch, Toyota engineers engines for generations of ownership, creating mechanical works that mature gracefully with time, like fine wine improving rather than deteriorating with age. The automotive industry has embraced aggressive downsizing, replacing larger, naturally aspirated engines with smaller turbocharged ones, producing more power under significantly higher stress. While competitors trumpet their 1.5-liter turbocharged engines with impressive horsepower figures, Toyota's larger 2.5-liter engines generate less peak power but maintain greater reserves of durability. This creates a tension between market expectations and Toyota's focus on lasting performance. Toyota's commitment to structural integrity becomes immediately apparent in their engineering choices. Their deep-skirted cylinder blocks extend significantly below the crankshaft centerline, adding material precisely where others remove it to save weight. Their crankshafts incorporate 8 balance weights instead of the standard 4 or 6, requiring more material and machining time but dramatically reducing vibration and extending component life by thousands of miles. These design elements function like the foundation of a well-built house, invisible to casual observers but essential for long-term stability. The oil circulation and cooling systems demonstrate similar over-engineering. Oil passages are deliberately oversized compared to minimum requirements, maintaining adequate flow even when partially obstructed by the sludge that develops as engines age. Cooling systems feature reserve capacity well above normal requirements, ensuring components remain within optimal temperature ranges even during extreme conditions. Toyota's approach to maintenance realities reveals their practical wisdom. Engineers design with the understanding that many owners will stretch maintenance intervals, sometimes significantly. Rather than creating systems that function perfectly only under ideal conditions, Toyota builds substantial margins that allow engines to survive even under considerable neglect. This acceptance of real-world conditions stands in stark contrast to competitors, whose engines often require flawless maintenance to reach high mileages. In practical terms, Toyota engines typically operate at just 60 to 70% of their theoretical maximum stress levels during normal driving. This creates an enormous buffer zone, protecting components from reaching failure points, even when pushing beyond recommended parameters. While competitors often design to meet warranty periods, Toyota designs for the vehicle's potential lifespan, often 15 years or more of regular operation. This approach creates a fascinating paradox. Like a craftsman who sacrifices flashy details for structural integrity, Toyota deliberately builds engines that appear modest on specification sheets, but achieve outstanding performance where it ultimately matters most: longevity. The company accepts the marketing challenge of selling vehicles with seemingly less impressive numbers because they understand the long-term value proposition resonates with consumers who prioritize reliability over bragging rights. Toyota's pursuit of reliability continues beyond the drawing board and into their manufacturing facilities, where tolerances are measured in microns, a fraction of the width of a human hair. In an industry where close enough often passes inspection, Toyota maintains standards of precision that most manufacturers consider unnecessarily strict and prohibitively expensive. This microscopic attention to detail happens in climate-controlled facilities where even a single degree of temperature fluctuation could compromise the exactness they demand. Step inside a Toyota engine plant and you'll find machines operating with almost surgical precision. The facility hums with quiet intensity, each station meticulously organized like a medical theater. The cylinder boring process exemplifies this meticulous approach. Unlike conventional manufacturing that might complete cylinder boring in 1 or 2 passes, Toyota employs multiple stages of increasingly fine machining. The final honing stage creates a crosshatch pattern on the cylinder walls, invisible to the naked eye but crucial for engine longevity. This microscopic texture, similar to an artist's carefully applied cross-hatching technique, forms tiny reservoirs that hold oil precisely where needed between the piston rings and cylinder walls, reducing friction to near theoretical minimums. This precision extends to every rotating component within the engine. The crankshaft, the heart of the engine's power transmission system, receives specialized polishing techniques that create a mirror-like finish on its journals. This smoothness dramatically reduces friction at critical bearing surfaces. While competitors often apply exotic coatings to achieve similar results, Toyota creates superior surfaces through machining processes alone, producing a natural finish that maintains its properties throughout the component's life. Temperature control represents another dimension of manufacturing precision. Toyota's machining centers operate in strictly regulated thermal environments, not for worker comfort, but because metal expands and contracts with temperature changes. By maintaining constant temperatures with variations less than that of a typical living room, Toyota ensures components machined at different times maintain consistent dimensions when assembled, eliminating microscopic misalignments that lead to premature wear. For certain high-performance applications, Toyota employs specialized plasma coating technology for cylinder walls. This process applies an incredibly thin layer of steel, measured in microns, that becomes permanently bonded to the aluminum engine block. The coating, thinner than a a sheet of tissue paper yet remarkably durable, provides dramatically improved wear resistance compared to conventional materials, creating the perfect interface between piston rings and cylinder wall. Quality verification occurs continuously throughout manufacturing. Each machined component passes through inspection stations equipped with coordinate measuring machines. These instruments use diamond-tip probes to map surface geometries with astonishing accuracy, detecting variations as small as 0.001 millimeters. Components deviating even microscopically from specifications are rejected, ensuring only perfectly formed parts continue to assembly. This level of precision carries significant costs. The specialized machinery, climate-controlled facilities, and extensive quality control systems represent enormous capital investments. The financial pressure to relax these standards remains constant, especially when competitors achieve acceptable results with less stringent processes. Yet Toyota's engineers consistently defend these exacting standards. They understand that microscopic imperfections compound over time. A bearing surface with minute irregularities experiences accelerated wear. A cylinder wall without the perfect crosshatch pattern won't retain oil optimally. These seemingly insignificant details make the difference between an engine that runs smoothly at 200,000 miles and one developing problems at half that distance. When parts are machined to such exacting standards, they fit together with almost perfect alignment, resulting in less vibration, reduced internal stress, and dramatically less wear during operation. Engines assembled from these components experience less internal friction, generate less heat, and maintain their performance characteristics for hundreds of thousands of miles. With components machined to near-perfect specifications, you might think Toyota's assembly process would rely entirely on robotics. Yet in their factories, you'll find something unexpected: a carefully orchestrated partnership between advanced automation and master technicians with decades of experience. This deliberate balance, which Toyota maintains while competitors rush toward fully automated facilities, might explain why their engines consistently outlast the competition. Before assembly begins, Toyota subjects each component to a multi-stage ultrasonic bath treatment. High-frequency sound waves create microscopic bubbles that collapse against surfaces, removing contaminants invisible to the human eye. This prevents premature wear between precision-fitted surfaces that would otherwise reduce engine lifespan. In the assembly areas, the Takumi, master technicians, represent Toyota's commitment to quality in human form. A typical day for a Takumi begins with calibrating sensitive tools and inspecting incoming components. By mid-morning, they're positioned at critical assembly stations, while their trained senses detect subtle abnormalities. When a connecting rod passes through their hands, they feel for the slightest resistance that might indicate misalignment. Their fingers trace along machine surfaces, identifying imperfections that even sophisticated sensors cannot detect. These craftsmen serve as the intuitive mind of the assembly process, while automated systems function as its precise muscles. Robots handle repetitive tasks requiring absolute consistency, applying exact torque patterns to cylinder head bolts or maintaining perfect alignment during component installation. Meanwhile, the Takumi apply judgment honed through decades of experience. They might pause to inspect a bearing surface or listen closely to the sound of a part being seated, making minor adjustments that transform a merely functional engine into one that will perform reliably for hundreds of thousands of miles. Toyota's assembly philosophy centers on jidoka, a principle that empowers every worker to stop production upon detecting quality concerns, creating accountability at every step and reinforcing Toyota's zero-compromise approach to quality. When an assembly worker pulls the end on cord, team leaders immediately respond, ensuring issues are resolved before they progress further in the production line. Traceability forms another cornerstone of Toyota's excellence. Each engine receives a unique identification code that creates a comprehensive digital record documenting every component, worker, machine, and test result. This allows Toyota to investigate issues years later, identifying patterns and implementing preventive measures across their production system. Specialized procedures prevent common failure points in engines. Hydraulic valve lifters undergo oil bleeding preparations that prevent momentary oil starvation during the engine's first start, eliminating a frequent cause of premature valve train wear in less meticulously assembled engines. The torque application for critical fasteners follows precise patterns developed through decades of engineering experience. Multiple stages of torque are applied to cylinder head bolts, main bearing caps, and connecting rod bolts in specific sequences. This methodology ensures even loading and proper sealing, preventing distortion that leads to premature failures. In Toyota's assembly ecosystem, robots and humans each contribute their unique strengths. Automation provides the steady, unwavering precision needed for consistent performance, while human technicians supply the intuitive judgment and sensory discernment that no machine can replicate. This synergistic partnership produces engines that routinely exceed their expected service life, often continuing to perform flawlessly long after competitors' engines require major overhauls or replacement. After the final torque sequence is complete, an engine's journey is far from over. That precision assembly is merely the prerequisite for what comes next: Toyota's relentless testing regime designed to expose weaknesses that no customer should ever experience. Unlike many manufacturers who sample test engines before shipping them to vehicle plants, Toyota subjects every single engine to a gauntlet of tests that simulate years of operation in just hours. Toyota's testing begins with the cold test, a procedure where each engine is mechanically rotated without fuel or spark. During rotation, sophisticated sensors monitor oil pressure, mechanical resistance, and acoustics to detect anomalies invisible to human inspection. These sensors can identify microscopic metal shavings, improper clearances, or assembly errors that would otherwise remain hidden until failure occurs years later. This initial screening transitions seamlessly into Toyota's comprehensive helium leak testing protocol. Helium, with atoms smaller than nearly any other gas, can escape through gaps invisible to conventional testing. Technicians pressurize each engine with this trace gas, while specialized detection equipment identifies even the most minuscule leaks that could eventually lead to oil consumption or pressure loss. Takumi Morita, a senior testing engineer with 30 years of experience at Toyota's Kamigo plant, explains, "The cold test catches most issues, but the helium test gives us true confidence. When we say zero tolerance for defects, we mean it literally. Gaps measured in molecules can trigger a rejection." Toyota takes quality verification several steps further. A significant percentage of engines advance to hot testing stations where they become fully operational. Fuel lines connect, ignition systems activate, and the engine runs while attached to sensors analyzing everything from exhaust composition to vibration signatures. This reveals potential issues like combustion irregularities under load, variations that might only become apparent after years of operation, but fall far below what even the most sensitive driver would notice. The most demanding evaluation occurs on dynamometers, where engines endure punishing conditions compressing years of stress into hours. Engineers rapidly cycle temperatures from cold start to full operating heat repeatedly. Load patterns swing from idle to maximum output in sequence no regular driver would ever impose. A quality control supervisor notes, "We don't just want to know if an engine works today. We need absolute certainty that it will perform flawlessly a decade from now, in any climate, under any reasonable operating condition." Toyota calibrates their testing equipment using prototype engines with deliberately manufactured flaws, slightly misaligned bearings, inadequate piston ring gaps, or cylinders a few microns out of round. These intentionally flawed engines serve as benchmarks, verifying that testing protocols can detect subtle deviations from perfection. When tests identify potential issues, Toyota initiates comprehensive investigations to identify root causes. Was it assembly variation, machining tolerance drift, material inconsistency from a supplier? Each anomaly triggers documentation and analysis, feeding into continuous improvement processes. This exhaustive approach creates significant tension within the production system. Additional testing adds time and cost, factors competitors often minimize. The financial implications are substantial, from expensive equipment to operational costs, including skilled technicians. Yet Toyota views this investment differently, not as a cost center, but as insurance against the greater expense of warranty repairs and damaged reputation. When an engine fails in service, the true cost extends beyond replacement parts to lost customer trust and brand reputation. Toyota's manufacturing approach represents a philosophy etched into metal. The results are impressive. While most manufacturers consider 150,000 miles successful, Toyota engines routinely surpass 300,000 miles of reliable service. Documented cases show Toyota Innovas exceeding 1 million kilometers, over 621,000 miles, while running on original internal components. This extraordinary longevity stems from Toyota's uncompromising approach at every stage, from metallurgic selection to final quality checks. The conservative specifications translate to exceptional durability on the road. That 15-year-old Camry still humming smoothly in your neighbor's driveway represents Toyota's dedication to creating engines that outlive trends and often the very bodies they power. In an industry focused on quarterly results, Toyota builds for generations, creating an engineered legacy that continues long after others have failed.